There you go. Thank you. On the context, so-called network virtualizations. Before I get a quick start, I want to take a quick survey to see how many people are getting familiar with those contexts before I move on. The first one, how many people are actually working on the Linux in this audience? Pretty much. Okay. Next one is about KVM and QEMU. Good. And the third one is about in the network domain, we call router switches. Pretty good. So M3, I guess Jim already mentioned about that one. I will skip that one. So it seems like many people here get familiar with the context. So I'll move at the pace much faster. There we go. Hey, Jim, doesn't move.
It's not working?
Yeah, it does.
You try the arrow? No?
No. Okay. Move closer.
No.
There we go.
Try that. Not. Let me put some new batteries in. How about that?
Okay, thank you. Yeah, so before we move on to the details of the context, I would like to see what did happen in the Linux before we move on to hypervisors. So we know in the Linux domain, there's a lot of things in the Linux kernels. We know there's L2, L3, and upper layer socket interfaces. In the layer 2, we typically have drivers, MAC layer bridge functions, and the L3 IP tables or other kind of functions move up to L4. Oh, sorry. Thank you. All the applications are typically communicate through the socket. There's still a few applications kind of using the raw sockets, but that's not many though. So most people in the application domain are pretty happy in the legacy so-called host applications. So that's perfect world until today. So once people start to introduce the so-called hypervisors in the Linux domain, I just gave a quick quote about KVM definition from the Wikipedia. I will not repeat it here though. So we know today, KVM supports multiple architectures, has common use in the network domain by many ISP as well as other service providers. Thanks. And this on the right side of the slide, people can see this is how typical people deploy the KVM in the Linux domains. As we can see from here, the KVM inherits most of things from Linux kernels, including many Linux functions, memory management, process scheduling, but it also inherits those kind of functions, so-called IP stacks. From high level, we can see when people deploy those kind of hypervisors, we get also TCP IP stack, I/O drivers from the Linux. On top side, in the VM, we also have TCP IP stack, I/O drivers. Those kind of thing is kind of an interesting point for today's topic. Yeah. Thanks. Before diving in further, we want to see how the traffic are basically being handled in the data centers. Typically, there are in the data center 3 typical kind of data traffic patterns. First one, the traffic goes across the VM, the virtual machine, within the host. Like from here, we have VM1 to VM2, the typical case in the data center. The case 2 will be the traffic goes from the VM in the host 1, go to another VM in another host. Another case will be the traffic goes from the aggregate to the core to the edge. Those are the typical data traffic patterns in the data center. Most of the traffic in today's data center are the top 2, we call the east and west kind of traffic. To better handle these first two cases, people kind of start to introduce so-called virtual switch. On the left side and the right side, people can see with the introduce of a virtual switch, the so-called help pin basically can be void in the case. There you go. Thanks. This is another slide about a similar case, but with the traffic goes from the VM in another host to another VM in another host. Again, here we also have the virtual switch on each of the hosts to gather traffic using either VXLAN, STT, or NVGRE protocols. In the further case, some company can also introduce virtual kind of distributed router. In the case, the further routing the traffic within the host. Among the hosts. you can see through this kind of introduction of the virtual switch or virtual router, the traffic can get optimized for the case of using the data center. Let's dive a little bit further into the virtual switch. In the case here, in the host, we can see virtual switch basically itself is a kernel module, like an OVS here, to handle most of the traffics. It has the function to face with the NIC cards to touch the physical world, also provides kind of virtual NIC to bridge up the virtual machine, the VM. OVS, I guess, is the most common one virtual switch being used in the open source community. But as we know today, OVS as a typical function can only in most cases be used for the endpoint visualization. What we meant for the endpoint is here, the VM will consume most of the traffic by itself. It's not going to be like the case for the network side. So this seems kind of perfect as well. But I put the question here, is really the perfect word? Now come to the concept, I guess Jim already introduced as well. Let's give a little bit further into what is the AFV. In the AFV concept, there's many kind of function modules. Here, like we have VNF1 all the way to VNF5. Each VNF basically provides kind of different function for network purpose. If you want to get the traffic from end node VM1 to the end node VM2, the traffic you want goes through a lot kind of VNF nodes in the middle. Those kind of provide network function. Network traffic eventually goes to the end node VM2. Those kind of VNF nodes I can build on top of a bare metal kind of servers, further on top of kind of virtualization layers. This implies a great things for the virtualization layers. So packet performance, that's the one we immediately think about. But also this kind of, for the NVA, basically introduce other kind of challenge we're going to talk down the road. If people need to know and want to know more about NVA, just gave a quick quote here. So by the way, as Jim mentioned, if there's any questions, just feel free to raise it during the presentations. Let's just still focus on the virtual switch side. What a typical switch performance challenge could be introduced by getting the concept of NFV? The four highlight points over here. First one is so-called NIC side, NIC and driver side. The second thing is about the virtual switch side. Those are typical performance bottleneck. The third one is from the virtual switch all the way send the traffic to the VM. This also typical bottleneck point from what we experienced before. Another one is one inside the VM. VM is the one is more like encapsulation, but there's a lot driver side in the VM. There's a lot kind of other kind of packet handling within the VM as well. So these are typical 4 points we know. Mm-hmm.
So these performance challenges you overcome by using the PCI SRIOV. You said that.
SRV is kind of one technology, but I do not think by itself can solve all the problems by itself. Thanks for the questions. So let me read the issues one by one, those challenges we mentioned before. The first one is the heavy host IP stack. This is a paper I read before about the PFRIM. I think people might heard about PFRIM before in this community. So on the left side, the author basically gave a quote to say how many kind of CPU cycles being spent on the typical Linux stack. On the right side, he gave a quote to say, he gave a right side to basically quote if they use PFRIM, what kind of performance improvement they will get. Just give a little bit highlight here. Based on these experiments, he basically quotes about 3,000 cycles for typical IP kind of packet go through IP stack in the Linux kernel.
Excuse me, is that 3,000 on one direction processing?
Sorry.
There's only one direction process.
Yes, for the one type of packets. Yeah, just a simple packet go from the driver side all the way up to the applications. This is a very quick example we evaluate as well from based on the NAND map. People might heard about NAND map before as well. It's kind of comparison with peripheral, but it's different though from its aspects. So in this way, we basically give a quick estimates about the performance-wise. We think by using NAND map by itself, we estimate the performance, but probably just cost about 1K cycles per packet. Yeah, people, if you want to know what is NAND map, just give a quote here. It's just very simple example that we want to see what the performance can be done, just compare with the native Linux host. The second issue is what we call two-stacked IP stack. Like I mentioned here, so people convert the Linux kernel itself directly into the hypervisor, become a KVM. That inherits the so-called IP stack. In the VM, in the most of the VM, we also have the TCP IP stack. So this two IP stack kind of overstacking working on each other can cause some problems. Like people mentioned about before, there's SRV. SRV can provide a way to bypass the Linux kernel in the host in a certain way. It kind of provide possible solutions. But in detail-wise, we found that can introduce other problems like VM portability. So it's basically it's one way, but it's not the ideal way. Let's move on. The challenge 3, or the issue 3, is from the old hairpin to the new hairpins by introducing the virtual switch. On the left side, this diagram people can we just refreshed about minutes ago. On the right side, we basically can see with the introduction of the virtual switch, it seems like the so-called hairpin can be reduced, but going down further into NFV situations, you can see the traffic might go from VM1 to another kind of VM functions, to go to another one, then go out. So in these kind of traffic patterns, the traffic goes through back switch and going out, back in and out several times. This puts heavy load on the virtual switch by itself. So in the case, we can see, because this is the reason, because VM, or the VNF node is not the endpoint consuming the packet anymore. The packet has to go through most of the VM in the cases. Issue number 4 is the one we are thinking that's got more troubles down the road as well. It's getting crowded kernel or hypervisor space. Today, there's in the virtual switch, we have some already kind of mature L2 functions. But beyond that one, people already kind of start to introduce distributed routings. Add MPLs, maybe add BGP, maybe add more packet classifier, redirectors, and other kind of load balancer. Further on top one, there's more kind of a layer 2 function down the road. So all those kind of functions, where to go? It goes directly into the hypervisors. So that gets more and more functions into the kernel, into the hypervisor. What that means? It's kind of like a recall to the kind of monolithic piece of the operating system. People here in this industry, in the network industry, kind of familiar kind of network OS. This kind of goes to the same mode like it happened before, got a kind of big, kind of monolithic OS. Further on top of that one, that also reduced the flexibility of add more functions into to fit for the network requirements. If I go to add everything into the kernel, that's if the two functions are kind of conflict from each other, that's very hard to do.
But you can configure them as modules, right? So they don't have to configure.
Yeah, thanks for bringing that up. Adding modules kind of a way to work it out, but it also add the instability for the system, for the kernels as well. And the same thing for here is when you add more functions to the kernel-wise, to hypervisors, that also makes the kernel kind of unstable. You remember, on top of the hypervisor, there's so many things are running down the road. There are a lot of VMs are actually running. You don't want to crash the kernel and crash the VM. Because once the kernel hypervisor gets more complicated, there's more kind of software issues down the road. Eventually, it will cause more issues. let's get a quick learning from existing approaches by many hardware vendors. So typical hardware vendors are not try to doing those kind of virtual switch in the way. They are doing another way. What are they doing? They are trying to introduce the kind of switch ASIC. This kind of ASIC can handle those kind of switching and routing functions. This is kind of a typical approach by a lot of kind of hardware vendors. In this way, they kind of still use Linux, but they're using Linux in a way to not basically leverage its own IP stack. But this kind of thing, we can know it work out in the way. In the case, by introducing virtual kind of a switch ASIC, they kind of provide the ASIC in the kernel. Actually, yeah, it's more like it's still in the kernel, but to provide the function captured in the switch ASIC. In this way, to provide a NIC, physical NIC facing outside, they also can provide VNIC facing to the VM side. So that way, it provides kind of a generic interface to most of the virtualized VM. This can definitely address kind of performance requirements and feature requirements by those kind of by the virtual machines. But it also introduces problem like portabilities and also feature velocity. Because for example, if you need a feature is not in the existing ASIC, like Broadcom or other kind of ASICs, you might wait for another cycles for it to get onto the market. So another thing is so-called what I put here is portability, is because once you introduce the ASIC, most of the time you might bind your VM to a certain kind of a physical port. So if you want to move the virtual machine to another host, you need to know that host might or may not have those kind of ASIC functions provided for your virtual machine.
So in this diagram, the ASIC is actually a piece of hardware and not a virtual?
In the host, yes. And in this case, there's a kind of some company already provide this kind of an operating system to basically virtualize the physical I/O and provide kind of virtualized I/O to the upper layer applications or other kind of virtual machines. Actually, there are many other hardware companies are kind of doing this kind of work right now.
Just, I guess, show of hands, how many people in this room are using ASICs woven into their solutions today? Okay, so a decent number of folks, not surprising.
Yeah, I know the Intel also has some kind of ASIC in this kind of situation as well. And basically, that's kind of one way to do it. But by using this way, we can see, just learn from hardware side, they are basically bypass the Linux kernel or the so-called IP stack in the hypervisors.
Now here is a big drawback is VM migration. Yeah, that's a very big drawback for that approach.
I think, from my work and some of our other guys can comment as well, virtualizing is one thing, being able to do live migration of these data pipes is another. Right?
The other issue here is you're having 2 transfers over PCI Express bus per packet.
Yeah.
And you just don't have the capacity in the PCI Express bus as usual to do that.
Yeah. Thank you. Thanks for bringing up that. So, but that's kind of way we learn from the hardware side. So move on to back to the software side. The virtual switch definitely provides kind of flexibility, what we need in this kind of network domain. But what we can do further beyond just those kind of, beyond try to kind of hit those kind of issues. So that's one way to solve those kind of issues. In this diagram, we are basically say we can use, I'm not sure, can we use the bit button to highlight?
The top one should be like a laser button?
Yeah. OK, there, go. So we could introduce SRV technology here in the NIC side. And another side, we can use QEMU. This is, I guess, the word, I guess people familiar in this area were familiar with QEMU as well. So in this way, we can use SRV to provide the separation of the access of the common kind of one adapter among different PCIe devices functions, and provide each of the functions to this VM, and provide network functions to another kind of virtual network service appliance. In this way, this provides just basic PCIe functions. This way will bypass the kernel itself in the hypervisors. So the traffic can go directly from the NIC cards to the VM or to the so-called network service appliance. Inside the virtual machine, people can provide the UIO, provide the basic, on top of UIO, they provide the IO functions on top of the guest kernel, and that traffic goes to the user-level applications in the virtual machine. So similar thing can also be handled by the network service appliance as well, to provide its own drivers and handle the traffic go direct from from physical NIC card to the appliance.
Quick question for you. If you employ this technique, do you then lose all of the functionality and policy that was previously being provided by the virtual switch? So things like encapsulation for VXLAN, how would that get done in this model?
Yeah, let me repeat your question. So by using this approach, do we lose any function from provided by virtual switch like VXLAN? That's actually that's good questions. So in this case, we just say the way we bypass those kind of Linux kernels. Definitely by missing this piece, we will lose the kind of virtual switch function as well. But most of those kind of NIC drivers or the NIC cards has some kind of switch functions as well. You can see here. Otherwise, it cannot demux those kind of packets as well. So this kind of implies we kind of use physical switch functions provided by the NIC cards. Yeah, thank you. And on top of that one, we also assume the typical encapsulation function can be done through those kind of appliances as well. But certainly, this will not solve those kind of issue at all. Let's move on to this kind of further kind of solution down the road. But before that one, to say why we're going to use DPDK for the network services. People in this community are quite familiar with DPDK. DPDK has, what we want is here. DPDK demonstrates those kind of packet performances, what we need for NFV. Nothing else we want yet from DPDK, but the most thing we want is the packet performance. From this diagram, we can see it can saturate the line rate even for the small packets. This is a diagram we actually get from Intel, so just quite a quote as well. The line rate will be 10G for now, and it could be 40 gig of NIC cards down the road. And another thing, the concept-wise difference from what we mentioned before is DPDK basically introduced kind of user-level, user space kind of packet handling beyond typical kernel space or ASIC. That's another thing we kind of a deep concept change as well. Further, on top of DPDK, we can leverage this kind of performance enhancement approach we just mentioned by Intel before, like the DDIO, like IOTLB, those kind of things, and the other kind of thing mentioned here. So by using this technology, by using this kind of concept-wise, we move to another step of way to use the DPDK for the NFV solutions. This is the way we introduce so-called user space virtual switch virtual routers. In this diagram, we can see we still bypass the kernel IP stack provided by typically provided by the hypervisors. In this way, the packet will go through the physical NIC card all the way to the user level switch or routers. And if there's a switching function needed by this kind of VM and virtual appliance, the virtual switch routers will guide the traffic to the VM. And the VM can also send the packet back to the virtual switch as well in the user space. And the virtual switch can also get the traffic out to the kind of virtual switch, to the virtual appliance as well. So in this kind of way, the kernel or the hypervisor backs to the way it was designed for, basically to provide the virtualization functions by skipping the network functions by itself. I will go a little bit slow for this one because this is a little bit more, there's a jump in the concept-wise. Inside the user switch routers, we can still use UIO technologies to basically provide the driver access direct to the physical NIC cards. Certainly, it can also benefit from the other kind of Intel DPDK solutions like DDIO, IOTLB, and PCIe solutions. In these solutions, basically all the VNIC is provided in the user space as well. This is also the difference. In this way, the virtual switch, if there's another VM get in, the virtual switch provides on-demand VNIC, and then provide the NIC functions to the new VM if there's a new one. Inside the VM, it's still the same technology we mentioned before. The QEMU can capture this kind of I/O packet, provides own UIO or existing I/O solutions, and give to the packet to the user space by itself. Certainly, inside the VM, people can still provide backend drivers or other kind of change, or can still use existing backend drivers. There's nothing change in the front-end drivers by itself within the QEMU, the guest kernels. By this approach, we can say it's kind of elastic in providing the I/O solutions, and can easily leverage those kind of multi-core solutions, because by itself, the user space kind of virtual switch, virtual router can scale itself by deploying on multiple kind of multi-core as well, because it's basically itself is on the user space. You can scale or scale up and scale down.
I have a question. For that approach, is any issue for the VM migration? For example, for destination host, we have the standard OS. Does it work or?
So let me repeat this. By using this approach, is this kind of change the way the VM can migrate, or still depends on the kind of common VIO solutions or VNIC solutions? And by using this approach, as I said, the VNIC is basically provided by the virtual router. The virtual router will still provide common existing I/O solution to the VM. So it's not kind of new. It may not provide new kind of NIC cards to the VM. But if you want, you can still optimize further. Can optimize the driver by itself for the KVM. But if you don't, this kind of driver is just the typical common drivers you can see today in the Linux domain, like VTAP, those kind of solutions.
What was that communication? Because you've got user space to user space. So are you just using a tap or a network bridge?
Yeah. So the question here, by using the user space to user space communication, but are we using the tap or what? In the very simple solution, we are using tap. It's kind of VTAP. But in the detailed implementation wise, it's kind of like Nahani cards. So people here might heard about Nahani cards. Yes, thanks. I guess you're from Intel. No, okay. So it's kind of a memory sharing kind of NIC cards, but it's different. But the Nahani cards goes further deep into the shared memory between the VM to VM. But so we do not go to that deep far. This kind of solution, we go basically to provide kind of shared memory access. But for the purpose of packet handling, though.
Yeah, but you've got tension there between breaking isolation and performance.
Yeah. So that's actually for the this gentleman just mentioned about the isolations as versus the performance as well. By using the Nahani drivers, it's kind of cause a lot of issues for the sharing. That's can cause kind of a security issues. So that's why another reason we kind of stay away from purely Nahani kind of approaches. We're using other approaches here. So we're going to contribute that back in the future to the DPDK communities. Thanks. By using this approach, definitely people have mentioned here, this will get very high performance. The same thing here. So that's why by using this approach, the performance is comparable with the hardware approach. It's much higher than the typical one you are using, or you are trying to use in Linux hypervisors by itself.
You're getting a tap to provide the same speed as your hardware?
It's almost. Yeah.
Your hardware.
So, by the way, yeah, the performance we are kind of experimenting on top of the Intel's Ivy Bridge boards. So I'm not sure what kind of board you might using, but on top of that performance, on top of that board, the performance is very high. So that goes another deeper into the stage direction wise. People are wondering, so if So in that way, people might think might still there are some kind of a traffic hairpin. In the case, might send traffic from one VM, goes to the user space virtual storage, then go back to another kind of VM. So there's still lightweight traffic hairpins in the case. If you really have that concerns, there's another kind of minor improvement into the approach we call the inter-VM direct packet pass-through. In this approach, the VM to VM can communicate directly on top of this kind of VNIC solution as well. As I said, we actually directly using this user space to user space kind of VNIC communication. So just extend a little bit further, this native VM will be able to communicate with another VM by providing a little new backend drivers. So how many people are actually working in the QEMU side? Okay, thanks. There are a few. So in the QEMU, there's backend drivers, the front-end drivers. Typically, people will not change the front-end driver because that's the one facing to the provided driver IO access for the guest kernel. But the backend driver is the one facing to the hypervisor side.
So this shared packet path, that's only for an environment where both VMs are trusted. Yeah. They trust each other.
Yeah, so the way the provider in this case only trust on the traffic wise, that they do not provide on the packet side. They do not trust each other on the other things beyond. So only handle the packet by itself. That's kind of reasonable because here, physical wise, this guy also sent the packet to here. They has to trust its packet sent over the wire as well. So by using this approach, certainly zero copy is possible. But that provides the basic zero copy from this VM to another VM is possible by using this kind of I/O solution as well. But this provides another further layer of trusting among those kind of between those VM as well. So,
yeah, I use QEMU, but I want to know: is there a parameter in QEMU that allows you VM to VM connection? How do you do that? I'm not familiar with that.
Thank you for that, Jen, to mention this question. So is there any other kind of parameter for use this kind of VM to VM direct communication in the existing VM, in the existing QEMU code? That's actually not available yet in today's QEMU code. That's the one we also try to get into the open source community as well. So this is a type of new backend driver, but it's a minor change. It's not big clumsy of code. It's what kernel we estimate is more like 1K to 2K line of code.
And it's available in open source?
It's not yet. We're still on the way to work it out. But after that one is available, it's just minor change on the parameters of on the QEMU commands to start a VM.
If you need some help, maybe have a volunteer to help work.
Okay, yeah. If you would help, that would be good. So we can definitely work with the open source community to get that part into the QEMUs.
Is that based on the previous shared memory QEMU drivers, where they attach a PCI config and you go read it and attach the shared memory that way?
Yeah, it has.
Something new.
Yeah, thanks for this. There's some guys to say how this can be done. Actually, it has some basic touch with the PCIe drivers. Also has some touch with the shared memory as well. That's why I said we kind of learn from the NAND kind of drivers, but that's just scale back to the way to provide purely memory sharing between those virtual machines. Just share memory only for the purpose of those packet pass-through. That's basically more like goes to the original concept of basic packet handling by the physical NIC card as well. So the shared memory is only for the purpose of packet.
Yeah, I understand that. I was asking a more specific question. Is this based on the work that was done in, I think, British Columbia about 4 years ago, who had a very similar concept?
That one we can talk about offline to see how it goes, but it's kind of on top of a lot kind of solutions people work together in the open source community, like NAND drivers, PCI, PF-RIN, NAND solutions, and as well those kind of vhost been mentioned about before. That provides us kind of a packet quick handling within the kernel as well. But there's many things among those areas, but this solutions basically leverage those kind of solutions, but provide quick, easy solutions on top of that one.
So that connection between the two QEMUs, like, there's no interaction between the overlay network then, right? If you need to switch it, so then, is that correct?
Yes. So another question is, so by provide direct VM to VM communications, we do not need another virtual switch or virtual router intercases. Yeah, yes, that's the way we think that's the solution. One of the solutions being provided on the table. In this way, if you definitely need high packet through from this VM to another VM, it can be done through these specific approaches. So in this way, you can even bypass the virtual switch functions provided by even in the user space. By the way, the user space switch itself is also high performance as well, because you can scale out. If you think you need more packet handling functions, you can scale out from 2 cores to 4 cores, or even further be provided as a resource available as well.
Is the direct linking between the two, is the performance you gained worth the potential for issues with migration or stability? So if one VM dies, how is the other VM going to handle that when they're directly connected versus leaving it all in the user space virtual switch router and then having it fully isolated?
So another question. Yeah. So another question is here. So performance-wise, besides performance-wise, is there any issues caused here by limits the VM kind of portabilities? So in this case, we still provide a generic I/O like VTAP. It's a simple case. So once the other VM, because these two VM commit to each other, if this VM dies out, this one will just send packet out. It just stuck here. It won't get anything impacted by another VM itself. So by the way, if this VM can still want to move out, it moves by itself. So by this way, so down the road, we think this provides more generic solutions down the road. For this VM, they do not need to care about either hardware or software solution. They just know it's connected to the VNIC. So this one can move out to another host. This still assumes it's connected to each other through the VNIC. And this VNIC down the line, it will be converted by this one to the physical one, go out, and it will be the same VNIC to this VM. But that's still approach down the road we can mention about here. That's what I will mention about future works. Future works, we want to. Okay.
So how do you handle the errors? I think the question was about an error, like a VM going away. Still thinking it has shared address space. How do you handle those kinds of errors? One of the VMs dies, the other one's in transit, sending data.
Yeah.
Shared memory space.
The shared memory basically as a resource can be basically what it means shared memory. But for this one, they don't know it's a shared memory. For this VM, it doesn't know it's a shared memory either. Shared memory is only in the concept of kernel or hypervisors. Basically, it's a resource being provided by the kernel, by the hypervisor itself. So these are kind of resources like other I/O or NIC cards being managed by the kernel itself.
The question is, do you preserve that shared memory, or do that shared memory go away, and the guest that remains informed about the memory going away? The question is, how do you handle that?
Yeah.
And how does that cleanly shut down that VM, come back, reclaim shared memory, and continue communicating?
Yeah. So
who's doing the management? Yeah, it's more a semantic question than a mechanism question.
Exactly. So let me just I think this gets a little deep further down into the VNIC implementation wise. So in the high level wise, I think, how many minutes do I have?
You're still good.
Okay.
You have
good
20 minutes. So
thanks. So here basically it's the case. As the I/O, this kind of shared memory as a VNIC is managed by the hypervisors. So once one VM goes away, this one still use it. As a resource-wise, it's still being available and be managed by the hypervisor provided to the VM. So this one can still send the traffic there. Just there's nobody able to consume that one. So at the end, it cannot push the packet as like TXRX. The queue is full. It's full, then you cannot send more traffic. That's the one case. So it will indicate the typical way to handle the backflow of the traffic-wise, it cannot go. So this queue, even though it could still send, it couldn't go out. But if both of the VM are gone, being provided by the VM, by the hypervisor, sorry, the hypervisor will be treated as the case. Nobody can consume the VNIC card. It will just remove it by itself automatically, or still keep there for next time when there's another kind of VM can boot up. still can use this VNIC. So in this case, the resource be managed by this by the hypervisor itself as well.
One more question. What's the expected performance gain going from VM to VM as opposed to going to the vSwitch?
Mm-hmm. So in this, what's the performance gain from the VM to VM versus goes direct to the virtual switch? So this compare with the one kind of virtual switch. If you compare with the OVS switch in the kernel, we will see this performance gain is much huge. The kernel performance we measure is much saturated of most of the VM packet consume capability by itself. Yeah.
I'm trying to figure out the one in user space.
The user space virtual switch. The user space, that's basically we are using similar solution here. That's what I said. The VM communicate with the virtual switch in the user space. You also use the same VNIC technology from the VM to VM as well. So has the same performance-wise on this link.
Okay. So basically, you're saying that if VM to VM is 1, then VM to vSwitch, then vSwitch back to VM2.
Yeah.
Is 2.
Yes. And by the way, yeah. So this way can also scale out if you need more. But this VM, typically, yeah, you could use multi-core as well. But this one scale much easier on the multi-core platform as well. And definitely, this one is a much higher performance than the link. That's why DPDK demonstrated that out. It can reach to, I think, to 40 gig single core as today. If you want to go to multi-core, yeah, that's more like saturated to 320 gig as well. Yeah, questions?
Okay. What kind of, so in the guest kernel, we have to do some routing decision to make differentiate between the situation that we can go to the user space switch or to other QM. So will it be a fully fledged IP routing there or just something very simple?
Yeah.
So how can we separate? Can we gain with putting the heavy routing decisions into the user space router and saving it in the guest kernel, or we have to have both of those places?
Yeah. The question here is if we are expecting the topologies connected. The topology connected this way, we do expect some kind of routing or switching functions be needed by this kind of VM in this area. So in this case, what kind of routing or switching function we expect from the VM? Because we assume, put back in the previous assumption, most of virtual machine today, we still assume it's endpoint packet consumption point or endpoint. In this case, it just need basic routing function to know where to go for the packet. And NAS is more like this kind of microservice appliance that has to have a kind of fancier, those kind of routing or switching functions for this kind of appliance as well. Or just like itself. This one has more routing, switching, or other kind of QoS and pairs, even other kind of functions on top in this area. So this one will only need simple routing switching functions, just to know where to route, because it has basic NIC cards and the IP addresses. Okay, so sorry, can I go first?
Yeah, I was going to say, for the performance aspect, a lot of the times people get really uptight about packet copies. And the zero copy part of the DPDK, which is really attractive, can become very difficult to manage. Kind of interrelated to that question about what happens if a VM blows up.
Yes.
And it was in the middle of having 1,000, 10,000 packets in its queues and playing with it, whatever. It seems like you have to have some really slick management software behind it. It's easy to use, right? Because the DPDK gets a lot of its speed from these, the receive queue DMA memory is on the same NUMA as the CPU that is processing that particular queue and the transmit queue. And all of that interrelated business is part of the solution that you guys are talking about putting in. Does it have a management aspect to it to make it, who's doing the cleanup when the VM dies and all of that?
Yeah. So I guess this get back to the question other gentlemen asked us before. Who basically is doing up those cleaning up for the resource as well? So actually, yeah, like you mentioned about before, the zero copy kind of provide much higher performance than the one, even than the approach we mentioned here. This one is potential. It's a zero copy is possible, but we did not go that deep further. So we just we have some copies in the case, because that's basically for the purpose of those kind of provider isolations as well. So yeah, as a resource-wise, what I mentioned here, basically it's a resource being managed by through the KVM hypervisors. So certainly you have through certain CLI to manage this as well. But basically the resource is own resourced by the hypervisor itself.
But you were talking about 120 gigabits per second. Does that have copies in the past?
No, the copy, the packets from here. The high performance from the physical new car to the user space switch routers. That's the much higher performance one.
So zero copy into the user space.
Yes.
Router, and then you're copying over to the VM.
Yes, there's a copy from here. Because this one they might use a different type of packet structure, what are things. So they have little way to do it, a different way to do it. For example, here they might expect K buffer. Here they expect something else. Now, this one might be just from Linux domain, might from another vendor. So they have the way to do it. But as long as they give a higher performance packet through from this VNIC, you'll be fine. Because most of VM today cannot consume the packet beyond 10 gig. So except for this kind of virtual kind of network service appliance, that's another question. But as of today, most of so-called appliance, even on the hardware side, they're still kind of within the boundary. Most of it still within the boundary of the 10 gig as well.
Let's say you dedicate like a CPU to a VM, like, or maybe like you also one CPU to a VM. Like, what's the maximum you've been able to push, like, in terms of bandwidth out of VM?
The packet push out of VM-wise, we have not tried out that one. But as I said, in the simple approach, we just try to saturate this one for the packet handling by itself. So today, just as long as it's 10 gig, that's where we're stopped. So we do not try to scale that further beyond just one core or just allocate one core or two cores to it. But we do allocate more cores to the user space routers, user space switches as well.
Also, with respect to the zero copy between the virtual switch and the VM, like, have you tried something like vhost user?
Yeah, that's our mention of vhost. Yeah, vhost we tried before. The vhost basically is another way. Basically, is vhost is another solution being provided today in the kernel. So is that one you mentioned about as a vhost? Yeah. So that one we experiment before. That's one that has a lot kind of use event FD basically does notification. There's a lot of system calls. That's the way we try to avoid that as well. So we try to go all the way to the user space. Instead of try to go, like use the QEMU to notify the vhost in the kernel through the system calls, and then come back through other ways. That provides certain shared memories between the kernel and the QEMU, but that's first it's a lot of system calls. Another way is the share between the kernel and the user space. That's another kind of further kind of issues down the road, cause the whole system is unstable though, because we might crash this one, but fundamentally we do not want anybody crash the kernel by itself. Yeah, thanks. That's back to you.
I'm trying to understand, like, so you have the motivation here is the zero copy between the areas, but I think that isn't there an OVS DPDK solution that could achieve that, and then you would basically gain the overlay, packet headers adding, removing, and stuff like that?
Back to the DPDK OVS solutions, yeah, that's one way to do it. Basically, get a similar concept as well. We get a similar approach, get everything into the user space. So that's basically to go to the basic functions. Today, those kind of user space virtual router, virtual switch provide more kind of network functions. That's what I was mentioning today. The DPDK OVS provides this kind of direction as well. It just need more work down the road. We mentioned here, need to support more I/O type, basically more physical I/O as well virtual I/O type, and also less intrusive I/O. What I mean here, the UIO certainly is one way of provide IO access as well, but this has provide back, basically rewrite the drivers being provided today. We think that's another way to provide less intrusive way to provide IO on top of existing IO driver in the Linux kernels. Another thing we think we needed is more like feature-rich user space more feature-rich functions in the OVS or in the similar user space switch or user space routers. Because by just put the OVS into user space, you still not have enough functions provided by the virtual switch cell. So there's more work down the road, like the diagram we mentioned here, multi-core expansion and multiple instance support for the multi-tenancies as well. So that's another reason we try to stay away from kernel virtual switch or kernel virtual routers as well. Because that basically it's hard to provide those kind of multi-tenancy management as well. That's another direction we're looking as well.
So what user space switches are you using open source ones or your own or both, or what is the?
Yeah, that's a good question. So are we using open source from the open source community or from the proprietary solutions? As of today, we actually built that one on top of DPDK plus some kind of open source solution, but internally there's a lot of kind of rich functions, kind of feature level enriched functions we are provided within the company proprietary solutions. Though we are looking the way down the road to contribute another way, just in the open source community. Yeah.
So sorry, is that proprietary then?
Yes, it's proprietary for now. Yeah, but we are trying to see when we can branch out to provide some more feature-enriched functions into the open source community.
So, I mean, the OVS one, do you not see that being very useful? I mean, what's the motive? I mean, I don't see a lot of work there. I do see some, but I mean, I do not see a really good harnessing between the two communities there.
Yeah, I do not. It's hard to speak back fully for the OVS community by itself, but from what we understand here, that's kind of function-wise, certainly it has some basic VXLAN functions, basic L2 functions. But that's why even today, there's some companies, even they try to integrate OVS, but they actually develop further on top of that one, much beyond its own original functions, to add more like a lot kind of L2 functions, add even distributed routers functions, add those kind of BGP functions on top of this one. So that's basically, it indicates there's kind of limited function being provided by OVS by itself. So in the summary, that's for my presentation is, so we think the monolithic hypervisor is not extensible by itself for the AM3 deployment. Certainly, it's good for the single host deployment. It's good for the certain type of traffic handling, but it may not be a good solution down the road for the AM3 expansion, though. The second thing we want to bring up to the community is that we think the Linux by itself, Linux KVM or other kind of hypervisor should focus more on the core functions, provide virtualization functions, and leave like process handling and the memory management, but leave those routings, network functions to the outside, make it more easier for expand in the future, make the hypervisor more stable in the future as well. That's why we think the other way is, we think user space IP stack provide more easier development, because it's in the user space, much easier to debug if there are any issues, and also provide higher packet pass-through performance we need, and also provide those compatible VM communication like people addressed before. Is the common VNIC? It's a proprietary. It's kind of proprietary kind of VNIC. As we mentioned, it's common one we provide as well. And the more fundamentally important is also much stable environment down the road, much stable and extensible solution down the road. Thank you.